Good morning, everybody. My name is Michele Lanotte. I'm an assistant professor in the Department of Civil Infrastructure and Environmental Engineering. Welcome to this webinar. This is the first one of 3 webinars today. I'm going to talk about sustainable solutions for the road infrastructure in Abu Dhabi. Usually, I give this presentation at the very end of my course in pavement design. Because I want my students to understand what is a sustainable solution in our area, road infrastructure, and I want them to understand how we can measure sustainability and check if a solution is really sustainable. So I usually start my presentation with my student by giving them a general understanding, a general concept of sustainability. We can define sustainability as the ability to meet the needs of the present without compromising the ability of the future generation to meet their needs. This is a very powerful concept. There is, in my opinion, a very nice example to understand this concept even better. The example comes from the Expo 2015 in Milan. At that time, the topic of the Expo was food and sustainability in food. And the example comes from the pavilion, the Swiss pavilion. What they did is they built a 4-tower construction, and in each of these towers, they put boxes with food. In one tower, you can see one of them here in the picture. In one of the towers, they put boxes with water, in another one coffee, in another one salt, and in the last one apples. And as soon as people start coming, visiting their pavilion, they told them, look, you can take all the foods and all the beverages you want, but please keep in mind that we are not refilling our towers by the end of the day. So whoever comes after you, next day, next month, must take something because they need something. So this is a really nice example to explain what sustainability really is. You have to think about your needs, your present need, but you don't have to forget the needs of who is coming after you. So this presentation is not really about sustainability in general. I want to focus the attention on sustainability for asphalt pavement and asphalt material. So for sustainability, we need to keep in mind that we have to preserve the surrounding ecosystem, meet the basic human rights, and achieve our scope, in our case, our engineering scope. And in order to do this, in order to find good solutions, we first need to understand the process of asphalt pavement and what is the life cycle of an asphalt pavement. There are different steps, different activities, different phases in a life cycle of asphalt pavement. The first one is for sure the extraction of the materials. Think about aggregates from quarries. Then we have to produce the bitumen. We have to produce the asphalt mixture, which is a mix between bitumen and aggregates, rocks. Then we have to construct our infrastructure. Then over time, during the service life of the pavement, we have to do cyclic maintenance and rehabilitation, and eventually destroy the old pavement structure when it's not good anymore, and then rebuild a new infrastructure. So in this life cycle, usually people focus on the production of bitumen and asphalt mixture. Why they do focus on this particular step of the life cycle of asphalt pavement? Because just to give a few numbers, we have more than 500 million tons of asphalt mixtures produced every year in the US only. Unfortunately, there are no data about Abu Dhabi and the UAE in general, so I'm going to provide some numbers from the US. There are more than 3,500 production facilities facilities for the asphalt mixture production, again US only, as an average, each of these plants emit 2,500 tons of CO2. So if you do a simple multiplication between this quantity of CO2 and the numbers of production facility, you can understand why the production of bitumen and the production of asphalt mixture is something that is of interest of many researchers. So we need to find solutions right at this step of the life cycle of asphalt pavement. However, as I will show you later, this is not the only important step, and there is something else that is also interesting to dig into as researchers. So what are the solutions to decrease the impacts of our materials in terms of environmental impacts, so in terms of CO2 and other gaseous emissions? So we have already in literature and put in practice actually many solutions. One of them is, for example, the polymer modified asphalt, which usually increases the service life of our pavement structures, and this solution is something that Abu Dhabi and the UAE in general is already implementing in their infrastructure network. Then we have another solution, the warm mix asphalt, which helps to reduce the greenhouse emissions during the production. Then we have the recycled asphalt pavement, so we can basically mill the old pavements, grind the material and treat the material and reuse the same material for new pavement structures. And then there are a whole bunch of industrial byproducts such as crumb rubber, paint sludge, sewing sludge, municipal waste that can be used in different ways. So in the next slides, I'm going to tell you about two of these solutions, in particular the warm mix asphalt and the use of crumb rubber from end-of-life tires, because these are the two technologies that here at Khalifa University, in cooperation with the municipality, we're trying to put together to take the benefits of the warm mix asphalt and the benefits of crumb rubber from end-of-life tires. So, what is a warm mix asphalt? Warm mix asphalt, or WMA, is a general term to describe asphalt pavements produced and placed at lower temperatures as compared to conventional hot mix asphalt. So in general, a hot mix asphalt is produced in plant at temperatures around 150, 170 degrees C, depending on the material that we are using. By adding to our mixtures different technology, wax-based additive or water, moisture-based agent, we can decrease this temperature by 20 to 30 degrees C. Obviously, if you produce a material at lower temperature, you need less energy during the production, so you have less impact on the environment. But this is not the only benefit that we can take from the use of warm mix asphalt. There are other benefits. Here in this slide, you see, in this picture in particular, you see on the left side a truck that is being loaded by hot mix asphalt, so produced at very high temperature. And on the right side, there is a warm mix asphalt. You can see by yourself that by using warm mix additives, we are also able to decrease the exposure to fumes of the paving crews and also minimize the heat exposure on already hot and warm days. This is of particular interest in this area. Imagine, go outside and imagine what's the temperature right now. We are around 50 degrees C. If you have on your side or you're working on site with a material that is at 170 degrees C, it's problematic. If you're working with a material that is at 135, 140 degrees C, is much better for the paving crew. So this is one solution that is beneficial from different point of views. And we are trying to put this solution with another environmental friendly solution, which is the crumb rubber from end-of-life tires. The concept behind this solution is very simple. We all have cars. We know that around the city there are trucks. All these vehicles have tires, and at a certain point they have to change these tires. So the old tires can be reused for other purposes. So the first thing we do is we take the whole car or truck tires, we remove from the tires the metal parts or the fibers that are inside and compose the whole tire, and we grind basically the tire and reduce to a powder. When it reduced to a powder, the rubber from end-of-life tires can be added to our asphalt mixtures. It can be added in different ways. One way to add crumb rubber to our mixers is basically first mix the rubber with the bitumen, so the hot black stuff in our road, and then this bitumen, rubberized bitumen, is then mixed with aggregates. Another way to do it is just to put the rubber as substitutions of the aggregates. So we can substitute a natural resource, the aggregates rock, with crumb rubber. And then we go on site and we pave our roads with this mixture, rubberized mixture. Good thing is that we don't need, even though this material is very different in terms of behavior compared to the traditional HMAs, we don't need any adjustment for our machines in field. So we can just use the same technology that we are using for traditional hot mix asphalt. And the number of waste tires that we can use is not negligible, is really significant. For an overlay of 5 centimeters for a new pavement, a new material, we can use up to 1,250 tires per each kilometer in one lane only. So this number is really not negligible. This solution is honestly not new. It has been used worldwide. In Europe, there are several countries where crumb rubber is currently being used to pave roads. In the US, there are several states that are currently using crumb rubber. I'm thinking about California, for example, where the use of rubberized mixture is a must nowadays. And people around the world have been sharing benefits due to this type of material included in hot mix asphalt. A few benefits are listed here in this slide. It seems that by using crumb rubber we can improve the cracking and rutting resistance of our mixture, and for this to explain how for example the rutting, the permanent deformation of a mixture can be improved, I put here a couple of pictures. Here on the left side you have a traditional HMA that has been tested for permanent deformation. So the two samples have been loaded axially in a machine, and you can see the deformation at the end of the test. You can see the bulge of these two samples. On the right side, you have the same type of mixtures, but in this case, we do have crumb rubber from end-of-life tires inside this material. And you see that the samples remain more or less as they were at the beginning of the test. So no really or just a little bit of permanent deformation that is not clearly visible over there. Then another benefit is that we have less aging. Our HMAs tend to age during their service life, and they age because of volatilization of certain compounds inside the asphalt bitumen. But when we add crumb crumb rubber from end-of-life tires, and these tires already include antioxidant. These antioxidants are dispersed into the bitumen, so we have less aging during the service life of our pavements. Then we can improve the skid resistance of the pavement surface, and some studies show that we can decrease the tire pavement noise up to 6 decibels, which is really a significant reduction of the noise due to truck and cars passing on our infrastructure. These are really well-documented benefits, but what we're doing here at Khalifa University is also dig into the assessment of the environmental benefits. And in order to do this, we are performing a life cycle assessment, LCA. Life cycle assessment is a standardized analysis to quantify the environmental impacts of a given product or a given system during its life cycle. The outcomes of this assessment, of this analysis, are energy consumption, natural resources depletions, emissions released in the atmospheres, and so on. So we are really looking at the environmental impacts due to the implementation of these new technologies. In general terms, a life cycle assessment consists of 3 steps. The first one is the definition of the goal and scope of the analysis. So we have to define what is the functional unit that we use as a reference. In our case, for pavement structure, it can be a cubic meter of structure or a kilometer of road. And then we have to understand which phases of the service life of our pavement structure we want to include in the analysis. When the system boundaries are in place, the second step of the analysis is the life cycle inventory. In this particular step, we go into each phase and we understand what are the activities that are composing each one of these phases. And for each of these activities, we collect information regarding materials, energy consumption, machines that have been that must be used in each of these activities. Then, by the use of some softwares like CIMA Pro or Gabi, or even customized Excel files, as we are doing here at Khalifa University, we get results in terms of impact about environmental impacts, so global warming potential, gross energy requirements of our material or the entire system. So this is in general how a life cycle assessment works. In particular for pavement materials, what we do is, first of all, again, we recognize the system boundaries. So for pavements, we have to include materials production, transportation of this material from point A to point B. A and B can be quarry and asphalt plant, or asphalt plant and the site where the construction is in place. So transportation in general. Then we have to construct our road. Then there is the use phase and the end of life. So all these phases are included in our system boundaries. So this is our life cycles of the pavement materials. Then, as a step 2, we have to define the activities, and we have to perform the life cycle inventory. So for materials, we go for the quarry extraction of aggregates, or for the asphalt bitumen production or the polymer production, and we collect data. These data can be primary data or secondary data. Usually it's very difficult to get primary data. Primary data are data that are directly collected in field or by interviewing people and crews that are working in a particular activities included in our system boundaries. Again, this is extremely difficult, and we can all understand why this can be difficult. So if these primary data are not available, we can use secondary data. There are inventories published online, so we can use these other sources to get information about the consumption of materials and energy and so on in our activities. Then we put all these things together and we calculate what are the impacts as in terms of air emissions, soil emissions, water emissions, and solid waste. So this is more or less the procedure that we are following. I want to share with you now a few results. So first of all, I want to share with you the results of the gross energy requirement and global warming potential of a traditional hot mix asphalt, one that has been used by years here in Abu Dhabi. So on purpose, I deleted the scale of these two graphs because the point is not the actual quantity of gross energy requirements of global warming potential. I just want to give you a comparison between materials. So the traditional HMA1 in this slide has in general terms a certain gross energy requirement and a global warming potential. So what if we add to this hot mix asphalt, a traditional hot mix asphalt, crumb rubber from end-of-life tires? What we see is that the new HMA with crumb rubber needs less gross energy and has a less global warming potential. So this is a good result. The benefits are clearly there. The gross energy requirement is almost half of the gross energy requirement of a traditional HMA. But as I told you before, rubber from end-of-life tires is not always the same. Think about the fact that the crumb rubber can come from car tires or truck tires. In nature, these tires are different. The material that is inside is different. So the effect of this material can be different. So what if we add a different type of crumb rubber to our hot mix asphalt? The HMA3 here includes a different type of rubber, and still we can see benefits in terms of gross energy requirement and global warming potential. So if one look at this graph and just comparing the different mixture, can say, okay, so crumb rubber is a good thing to add to my HMA because there are benefits in terms of environmental impact. However, it must be, we have to do another step in the analysis, because it's true that not all the crumb rubber are the same, but also we do have different technologies that we can use to add crumb rubber in our HMAs. I told you at the beginning that we can add crumb rubber by mixing first with bitumen, or we just can add crumb rubber as it is in the mixture without previous mixing with bitumen. So what if we change the technology, we change the way to use crumb rubber, and we add crumb rubber in a different way? And this is HMA4. And you see here that the HMA4 has higher gross energy requirement and higher global warming potential than a traditional HMA. So usually my students say, how come we are still using a industrial byproduct, we are still using a waste? Why now the gross energy requirements and the global warming potential are higher than a traditional HMA? To explain this, I have to go back to this slide and highlight the use phase. This is something that we are particularly interested here at Khalifa University, because the use phase is extremely important when we do a life cycle assessment, because if your material does not perform good, you need soon to be replaced. So if you produce a material, still it has crumb rubber inside, whatever other technology you want to consider, okay? But if the material does not perform good in field, you need to substitute this material sooner than another HMA. So when you substitute that material, it means that you have to produce other materials. So this is not good in terms of impacts for the environment. So the use phase is extremely important. And in order to understand a little bit more about the use phase, we are using some distress prediction model. So we do tests in our lab, we measure, we understand what is the behavior of the different materials under load, and then we use some distress prediction model to compare the material and forecast the service life. Obviously, if a material has a service life, forecasted service life of 20 years, and another one has a forecasted service life of 10 years, it's implicit then the second one will have higher environmental impact, because you have to get rid of it sooner than the other one, and you have to produce other material and substitute the first one, the one that you put in the first place. However, by looking at models is one part of our job. What we are doing in cooperation with the municipality of Abu Dhabi is a real implementation. So we have studied some hot mix asphalt with crumb rubber in our lab, and the municipality was willing to construct a pavement section, a real scale pavement section on the highway E30, which is a highly trafficked track road just outside Abu Dhabi. We constructed the road and we divided the road in 5 sections. The blue one at the very beginning on the right side here in this picture, this section has been constructed with a traditional material commonly used here in Abu Dhabi. And then there are other 4 sections, 2 of them with crumb rubber, and other 2 have been constructed with polymer modified bitumen as a comparison. And what we are doing is from time to time, once or twice per year, we are going on site to do some measurements of the distresses on the pavement structure. Plus, we are conducting experiment on the same materials in lab, and you can see here in these pictures we are studying about the cracking of asphalt mixtures or the permanent deformation of these asphalt mixtures, and we are also trying to use different crumb rubber, different sources to understand how they change the performance of these materials that can be one day implemented in field here in Abu Dhabi or in the UAE in general. So thank you for your attention. I'm done with the presentation. If there are any questions, please go ahead and ask. Okay. First question is, for you, which solution is the most useful for Abu Dhabi? This is a very nice question, and we can even go for another presentation by discussing the answer for this question. We have to understand one thing. Our material, the hot mix asphalt, is a material that is highly dependent on temperature, for example. So here in Abu Dhabi, here in the UAE, due to the environment that we have here, all the distresses that we have on our pavement structure are related to the high temperatures. So a distress that is directly correlated to high temperature is rutting, permanent deformation. So any solution that can enhance the performance of our hot mix asphalt for this distress is a good solution. Now, crumb rubber has been of high interest for the municipality of Abu Dhabi because think about the rubber is a highly elastic material. So it's implicit that the permanent deformation due to the presence of that material, that byproduct into our pavement must be way less than the usual traditional HMA. So that's why crumb rubber from end-of-life tires can be, in my opinion, one one of the best material that can be used, one of the best solution that we can use. Then the second question, is secondary data as important as the primary? As we all know that the primary is difficult to collect. Yeah, I mean, usually if you have primary data, you can put a big smile on your face and go ahead with your analysis. One good thing in our case, since we paved the road, is that we were able to discuss each and every step of the process with the people that were producing the material. So we did collect some primary data for our study. But in a way or another, you have to do the analysis, and you have to adjust maybe the analysis to your environment when you don't have the primary data. So I do agree with the fact that primary data are way better than the secondary data, and if you do have primary data, your analysis will be way better than the other one. But at the end of the day, if you want to compare material A versus material B, you have to go for secondary data. Good. So we're done for this presentation. Thanks for your attention and have a nice day.